Welcome to lecture number 4 of Special Relativity for UPSC CSC Physics Optional. So, Vm, what is Vm? C vector minus V vector. And Vm vector was the velocity of light with respect to object frame, and C was the velocity of light in ether frame. C vector was the velocity of light in ether frame. V vector was the velocity of object with respect to ether. And over here the object is Earth. What is the object over here? The object is Earth over here. Okay. If this we have already derived in the previous lecture, this particular expression we have already discussed in the previous lecture. If you haven't watched the previous lectures, you can go to the link in the description and start watching from the first lecture. But in third lecture I had told you this particular formula. Okay, and over here in this formula object is Earth. Okay, so from this formula we can certainly write that Vm plus V vector will be equal to C vector. Okay, this Vm vector plus V vector will be equal to C vector. It is quite obvious, right? Because this Vm, this V will come to the left hand side and will get added to this Vm vector. So Vm vector plus V vector will be equal to C vector. Now this Vm vector can be V perpendicular and it can be V parallel. Why it can be V perpendicular and V parallel? It can be V perpendicular and it can be V parallel. Only two are possible because we are sending two light beams perpendicular. We are sending two perpendicular light beams with respect to Earth's frame. With respect to Earth's frame, we are sending two perpendicular light beams. One of the light beams, you can have a look over here. One of the light beam is parallel to the velocity of Earth in ether, and another light beam is perpendicular to the velocity of Earth in ether. Okay, so such two perpendicular light beams we are sending. Okay, so that's why this Vm can be only two values: V perpendicular, V parallel. This is just a kind of denotation. We are just denoting like this. We are just denoting like this because if we denote like this, it will be very convenient to us. It will be very convenient to us. That's why. Okay. Let's find out V perpendicular and V parallel. So V perpendicular, you can have a look in the figure. Okay, you can have a look at this figure. V perpendicular will be directed in this direction. C vector will be directed in this direction. V vector will be directed in this particular direction. So from triangle law of vector addition, we can say V perpendicular vector is equal to C vector minus V vector. We can say like this. So the modulus of V perpendicular vector, the modulus will be equal to square root of C square minus V square. Why will it be equal to square root of C square minus V square? Because this is the right angle triangle. So C is the hypotenuse, V is one side and V perpendicular is another side. So V perpendicular vector magnitude will be equal to C square minus V square by hypotenuse, by Pythagoras theorem. Okay, by Pythagoras theorem we can say it like this: V perpendicular is equal to square root of C square minus V square. Now in a similar fashion we have this particular thing, the light signal which we had sent parallel to Earth's velocity in ether. So V is the velocity of Earth in ether, and we have sent this particular signal in the parallel direction. Okay, this was in perpendicular direction and this is in parallel direction. This signal is in parallel direction. So V parallel will be equal to C vector minus V vector, as already learned in the previous lectures. So V parallel vector magnitude will be equal to C minus V, because this is forming a straight line. So V parallel will be equal to C minus V, because V parallel plus V will be equal to C, because it is forming a straight line, and by the collinear point theorem. Okay, this vector plus this vector will be equal to C, so this vector will be equal to C minus V. Okay, although while writing in vector form we are writing like this, so because it is forming 0-degree angle, so it came out to be as it is. Okay, so V parallel vector magnitude is equal to C minus V. Now over here C vector's magnitude has been written as C, V vector's magnitude has been written as simply V. Okay, this is a very common notation. You are all aware about this notation. Okay. Similarly, we can find the speed of light in case they were directed opposite. They were moving opposite to the original directions. So if suppose this V perpendicular, instead of moving in this particular direction, that is upwards, instead of that, if that V perpendicular is downwards, suppose, then what will happen? Okay, then what will happen? This is the thing which one needs to find out. And similarly, instead of this where V parallel like this in this direction, instead of that, if the V parallel is directed in this particular direction instead of this direction, then what will happen? That also one needs to find out. Okay, so how to find that out? Let us have a look at the next slide. We will understand from the next slide this particular concept. Okay, so V perpendicular is directed to the opposite direction. Okay, it was directed upward in the previous slide, now it is being directed downward. And why are we doing all these calculations? We are doing all these calculations because we want to understand Michelson-Morley experiment. And in Michelson-Morley experiment, if we want to understand it properly, we must know these calculations very properly. Only then we will be able to understand properly. So that's why we are doing these calculations. Okay, so V perpendicular, it is in downward direction. V minus, so it is, as this V perpendicular is in downward direction, that's why I am writing it to be minus perpendicular, because it is directed opposite to this. It was directed upward and this is directed downward. So I am writing, instead of V perpendicular, I am writing V minus perpendicular. Okay, similarly V parallel was directed rightward. V parallel was directed rightward. So I am taking V minus parallel. I am taking V minus parallel to be directed in leftward direction. That is opposite of rightward. So it is directed leftward. Okay, and the earth is as it is. The earth is moving as it is in rightward direction with orbital velocity V. Okay, so the earth is as it is. Now let us see what happens to the vector formulas. So V minus perpendicular vector directed to the downward side. C is directed like this, V is directed like this. Okay, similarly V minus parallel will be directed like this, V will be directed like this, and C will be directed like this. How are these coming? These are coming from the vector law. Okay, triangular law of vector addition. From those things we are looking at these things. Okay, so actually this is the velocity of the light signal after reflection from mirror. Where the mirror is situated you will come to know later on, but this is the reflected beam in Michelson-Morley experiment, and this is also the reflected beam in Michelson-Morley experiment. Okay, so this is the velocity with respect to earth, velocity of reflected beam with respect to earth, and this is also velocity of reflected beam with respect to earth. Okay, so you must be aware that this velocity and this velocity are the velocities which are with respect to earth. Okay, so we are finding out these things so that our calculations becomes easy. So after looking at this particular triangle, what will happen? V minus perpendicular vector will be equal to square root of c square minus v square, and similarly V minus parallel vector will be equal to c vector minus v vector. Looking at these two figures we can certainly say this. Okay, so this formula is common. Over here right angle triangle is being formed, so V minus perpendicular came out to be same. It came out to be same as the magnitude, I mean the magnitude of this particular vector is same as this particular thing. Okay, the magnitude has come out to be equal to this. That's what I was saying. This is the fact which I was telling. Okay, but in case of V minus parallel, C vector minus V vector, now when you subtract this V vector, it is already located, it is already opposite to the direction of V minus parallel. Okay, V minus parallel is directed leftward, and so from here what can one say? One can clearly say that C plus V, from the geometry of the figure, C plus V will be equal to V minus parallel. Okay, magnitude wise. So magnitude wise V minus parallel vector magnitude will be equal to C plus V. Okay, so this is the thing. We are taking leftward direction to be positive, then rightward direction will be taken as negative, and that's why all these things have come. Okay, so you can certainly have a look at this figure and you can certainly reach to this particular conclusion. Okay, so let us learn about the Michelson-Morley experiment. So using the concept which has been given on the previous slides, this relative velocity concept. Okay, using this concept Michelson-Morley designed an experiment, and this experiment was meant to verify the ether hypothesis. This also we have already discussed. Now in this particular figure, these dotted lines might be visible to you. Okay, these dotted lines might be visible to you. So I request you guys to consider these dotted lines to be straight lines. Okay, because those are not appearing like straight lines, but those are straight lines indeed. So consider this to be a straight line, consider this to be a straight line, and also consider this to be a straight line, and also this to be a straight line. These dotted lines show the ray of light. These dotted lines show the ray of light. Okay, so this S is a source, monochromatic source of light. Okay, monochromatic beam of light is being, and it is an extended source, by the way. It is an extended source. Okay, extended source of light, not a point source, extended source indeed. Okay, and monochromatic. And what? And monochromatic. This also you should remember that it was monochromatic light. Okay, so after learning this S is the source of monochromatic light. So a ray of light will go from here. Now this M is half silvered mirror. This green mirror M is half silvered mirror. Okay, and these M2 and this M1 are fully silvered mirrors. So these M1 and M2, almost 100% light is being reflected from M1 and 100% light is being reflected. Okay, almost 100% light is being reflected from M2 and almost 100% light is being reflected from M1. Okay, but this M mirror, okay, this mirror M is only half silvered. Okay, so if you want to show it half silvered, you can just make this line to be a little bit thick. Okay, this backward portion of the mirror M is polished with silver, but half polished, not fully polished with silver, half polished. So what happens in half polished mirror is that if suppose there is a mirror like this which is half polished, okay, it is only polished in the backward side, okay, in the front side it is normal. So what happens is that when the light beam is incident on this particular mirror, 50% of the light beam passes and 50% of the light beam is reflected. Okay, so this is the thing. With half silvered mirror, this is the thing, that 50% of the light will be transmitted, that is refracted. Okay, refracted, or you may say transmitted. Okay, 50% is refracted and 50% is reflected. Okay, 50% is reflected. Okay, this is the main characteristic of a half silvered mirror. This is the main characteristic of a half silvered mirror. So this mirror is that kind of half silvered mirror, this green mirror M. Okay, this beam of light will be incident on it. Okay, half of the intensity will be reflected like this in this particular direction. Okay, and half of the light will be transmitted from here. Okay, that is refracted from here. So this particular, after falling on this mirror, this is the direction which the reflected beam from this mirror M takes, and this is the direction which refracted beam from M takes. Okay, this is the direction which reflected beam from M takes, and this is the direction which refracted beam from M takes. Okay, now after getting reflected from mirror M2, this particular beam will go and it will fall on this mirror M2. So after falling on that mirror M2, okay, after falling on that mirror M2, what will happen? After falling on that mirror M2, this red colored beam which is going upwards will now come downwards in the form of this brown colored beam. Okay, and this red colored beam which was moving rightwards will reflect from M1 and it will come in this direction which has been shown in brown color. Okay, so this is the thing. Now this particular beam, brown beam, will fall on this half silvered mirror M, and a part of it will be reflected, just ignore that. Okay, and this mirror and a part of this will be transmitted, so it will come over here. Okay, so this brown colored beam comes over here, and similarly this brown colored beam, when it was moving like this, it will reflect with the silver face on over here, and again it will also travel in this direction itself. Okay, what happened to the, now when this brown beam was coming downward, it was reflected and it was transmitted. So we considered the transmitted one, we neglected the reflected one. And when this brown beam was coming like this in the leftward direction, we considered its reflection and we neglected its refraction from here and going in this direction. Okay, so these beams only reflection was considered, and these beams only refraction was considered. Okay, because over here is the observing telescope. That's why it was done like that. Because over here is the observing telescope, and observing telescope is not present here. Okay, so the reflected beam of this will go over here. We ignore that, and the reflected beam of this, like this. Okay, it will go in this direction. We neglected that. Okay, and we only considered the reflected portion of this beam, and the refracted portion of this beam, and both of them come out to be in this direction and coming towards the telescope T. Okay. This mirror M has been kept at 45-degree angles. Okay, so this particular angle is 45-degree angle. Let me mark it with some other color. Okay, so this angle is 45-degree approximately. Okay, 45-degree. And if this angle is 45-degree, then if you draw a normal, if you try to draw a normal over this mirror M, so the normal will look something like this. Okay, the normal will look something like this. And after looking at the normal, you can certainly say that this angle will also be 45-degree. This angle will also be 45-degree because the downward angle, this angle was 45-degree. That's why this angle will also be 45-degree. So, angle of incidence, this will be what? This 45, yellow 45 is angle of incidence. And after reflection, the beam will go like this. Okay. So, this is also 45-degree. Okay, got it? So that's why the mirror M has been kept in 45-degree angle, so that the beam which comes like this, goes in direction upward and goes in a direction straight. Okay, that's why this mirror has been kept at 45-degree angle. Okay, so this is the phenomena. Let me erase some things because it is getting too much cluttered. Okay, oh, so now it is okay. Okay, so this 45-degree, after you draw the normal over here, it will be 45-degree angle of incidence, so angle of reflection will also be 45-degree. So the beam will go like this, beam will come back. Okay, half of it will go like this and half of it will be reflected back from here. The beam will go like this, come back, and it will go like this also, and it will go in this direction also. These directions, both beam we neglected. We only considered the downward side direction beam, and those beams reach the telescope T. Okay, so hopefully you understood why this 45-degree angle has been chosen, so that this beam is incident normally on mirror M2 and this beam is incident normally on mirror M1. That's why this mirror M, that's why this half silvered mirror M has been kept at 45-degree angle. This is the complete apparatus. This is how Michelson-Morley experiment apparatus looks like. Okay. Let us learn about the time taken by the beams to travel in the Michelson-Morley experiment. Okay, so have a look at this particular figure. Okay, so I have basically redrawn this particular apparatus. I have redrawn this particular apparatus in a simpler form. This has been redrawn in a simpler form. Now, what happens is that there is an extended source of light present over here. Rays of light are coming like this, and suppose you are considering a single light ray, then what will happen? The light ray will come like this. Okay, as the mirror is half silvered, so it will get reflected and it will get refracted in this direction. Then the reflected part will move like this. It will get reflected from here and it will get transmitted in a straight line, and it will also get reflected from here. But this reflection we are ignoring and we are just considering this transmittance. The part of the beam which was going like this, after getting reflected from here, it will go like this. It will reflect from M1, it will come back, it will get reflected here, and it will get reflected here, because M is half silvered. So there are two beams which are reflected in this particular direction. Okay, one coming from here and coming like this, and another coming like this and coming here. Okay, so one is refracted from here and one other is reflected from here, this side. Okay, so that is how two light beams are reaching over this observing telescope which has been kept here. So two light rays are reaching here in this particular direction. Okay, and we have neglected two light beams which are going in this particular direction. Okay, we have neglected them. Okay, two light beams, one reflected and one refracted, we have neglected, that go in this direction. We have neglected them. Okay, hopefully you are getting the things. Now, if you want to calculate the time difference between this, the traveling of this beam and traveling of this beam, if you want to travel the time difference, if you want to calculate the time difference in traveling, you can certainly neglect this particular time difference, because after here the two rays are parallel, the two rays are coming together. Okay, after getting interacted by this mirror M, the two rays are coming in the same direction. Okay, So as two rays are coming in the same direction, in this part the time required of by both of them will be the same. Okay, but while traveling like this and coming back up to here, and while traveling like this and coming back up to here, the time required will be different. Although after that they travel together, so time required will be same, but when they will travel like this and will come back, it will take different time, and when this will come go over here and it will be reflected and come, it will come like this, the time required will be different. Okay, so the time in perpendicular direction, okay, the direction of Earth's velocity is what? The direction of Earth's velocity is this. Okay, orbital velocity of Earth is in this particular direction, rightward direction. Okay, and this particular direction is what? This particular direction I am showing over here. This is perpendicular direction to velocity of Earth, and this direction is parallel to velocity of Earth. Okay, so let us calculate the time t parallel taken for the light to travel to and fro. Time t parallel, which will be taken over here. Okay, so time t parallel taken for the light to travel to and fro. Okay, so t parallel will be required. It will go like this and it will come back. Okay, so time t parallel taken for the light to travel to and fro in the parallel arm of length L. Let us assume that this particular arm has a length L. Let us assume that from here till here, from this particular point up to here, the length is suppose small l. This particular length is suppose a small l. Let us suppose. Then what will happen? The time t parallel will be calculated in this particular manner. Time t parallel will be calculated like this: L divided by c minus v. Okay, and these four values which are in brown circle. This particular value square root of c square minus v square. This particular value square root of c square minus v square. This particular value c minus v, and this particular value c plus v. We have already calculated in the previous slides of this lecture. Okay, so we have already calculated those values. Okay, now if we want to find out time t parallel, then what will happen? Distance is L and speed is c minus v. So L divided by c minus v will be the time required to go from here up to here. So L divided by c minus v. L divided by c minus v is the time required for going like this. Okay, and the time required for coming like this will be L divided by c plus v. Okay, time required for coming like this will be L divided by c plus v. So L divided by c plus v. Okay, so we are adding these two times to find out the time t parallel. So it will be for going up to here t divided by c minus v, and for coming like this t divided by c plus v. Okay, L divided by, not t, sorry, from going for going from here up to here, L divided by c minus v, and from going from here up to here, L divided by c plus v. Okay, so L divided by c minus v plus L divided by c plus v. This is the t parallel. This is the time taken for the light to travel to and fro in the parallel arm. Okay, and why is it being called as parallel arm? Because it is parallel to the direction of Earth's velocity v. Okay, so t parallel is L divided by c minus v plus L divided by c plus v. Take L common outside from here, so we have taken L common outside. Okay, so what will happen? Let us take LCM. Let us take LCM of c minus v and c plus v. So LCM will be c square minus v square. Over here in the numerator, c plus v will occur. So c plus v has occurred over here. C plus v is in the denominator. So in the numerator, c minus v will be there. So c minus v is there. Okay, this v and this v will cancel out, and it will be L is common over here. C plus c, c plus c will become 2c. It will become 2c, and divided by c square minus v square. So divided by c square minus v square. Okay, this is the t parallel. This is what t parallel. Now let us take c square common from here. Let us take c square common outside from here. Okay, so it will be 1 minus v square by c square, and c square will come over here. Okay, so 2c has been written along with this. 2c has been written along with this, and c square has been taken common outside from this. So 2lc divided by c square is multiplied by 2lc divided by c square multiplied by 1 divided by 1 divided by 1 minus v square by c square. 2lc divided by c square multiplied by 1 divided by 1 minus v square by c square. So I have cancelled this c with this c. So c, it will be c square. So c square is c into c. So one of the c will be cancelled. So it will become 2l divided by c. 2l divided by c multiplied by 2l divided by c multiplied by 1 divided by 1 minus v square by c square. Okay, so this is the thing. Now 2l by c will remain as it is. 2l by c has remained as it is. 1 divided by 1 minus v square by c square. Over here it is written like this. So 1 minus v square by c square to the power minus 1 will happen over here. Okay, because this particular entire term is there present in the denominator. This entire term is present in the denominator, right? As it is present in the denominator, also when it will come in the numerator, power minus 1 will occur. Okay, so 1 minus v square by c square to the power minus 1 has happened over here. Okay, it has occurred. Now you already know that v, that is the orbital velocity of earth. Okay, v, that is the orbital velocity of the earth, it is of the order of 3 into 10 to the power 4 meter per second. Okay, and what is the velocity of light? It is 3 into 10 to the power 8 meter per second. Okay, now this ratio v by c, clearly this particular ratio v by c will be very small ratio, approximately it will be approximately equal to 10 to the power minus 4. Okay, approximately. So v square by c square will be of the order of, it will be of the order of 10 to the power minus 8. Okay, it will be of the order of 10 to the power minus 8. Now 10 to the power minus 8, 10 to the power minus 8 is very small as compared to 1. It is very small as compared to 1. So what will happen? Let me tell you what will happen in that scenario. Okay, so v square by c square is clearly very small as compared to 1. Okay, so what will happen in that scenario? You already know that 1 minus x to the power n. Okay, 1 minus x to the power n when x is very small as compared to 1. Okay, very small as compared to 1. What is it equal to? It is equal to 1 minus nx. Is equal to 1 minus nx, right? First approximation. Okay, binomial theorem, first approximation. So 1 minus v square by c square to the power minus 1. So 2l by c remained as it is, and this minus sign, this n, as it is nx. Okay, so minus 1 will come inside and it will become 1 plus v square by c square. We have simply applied this particular formula. We have simply applied this particular formula of binomial theorem. Okay, 1 minus x to the power n when x is very small as compared to 1. So it will be 1 minus nx. It will be equal to 1 minus nx. That is, the power will get multiplied with this and it will be written like this. Okay, the next terms, the terms next to this, that is x square, x cube and all those things in the expansion, those things will be neglected and only the first expansion will be considered. Okay, so this is the meaning of this particular thing. Okay, so hopefully you got the meaning of this. So how you got this? So from here we have got this, that t parallel has come out to be equal to what? T parallel has come out to be equal to 2l by c multiplied by 1 plus v square by c square. This is the value of what? This is the value of t parallel. 2l by c multiplied by 1 plus v square by c square. This is the value of t parallel. Let us calculate the t perpendicular. Okay, so time t perpendicular. Now we had just calculated time t parallel. Similarly, we are calculating time t perpendicular. So time t perpendicular taken by the light. So what will be t perpendicular? This particular direction. This going from this up to here and then coming back over here. Okay, this is length L and this is square root of c square minus v square while going upwards, and the same is the speed, square root of c square minus v square, same is the speed while going downward. We have already calculated this in the preceding slides of this lecture itself. So if you consider the length to be L, so while going, L divided by this much will be the time required, and while coming down, L divided by this much will be the time required. So you can clearly say that for v or t perpendicular, 2l divided by square root of c square minus v square will be the expression. Okay, why 2l? Because the speed is the same, so you can take the distance to be 2l. Okay, l plus l, 2l divided by, speed is constant while going up also and while going downward also, speed is constant, square root of c square minus v square. So 2l is the total distance, speed is constant, which is square root of c square minus v square. So time will be l divided by square root of c square minus v square. That will be the total time. Okay, time will be 2l divided by square root of c square minus v square. That is the time perpendicular, time in the perpendicular direction. Now let us take c square common from here. If you take c square common outside from here, it will become c, because there is a square root sign, so it will become c. Now after taking c square common from here, this will turn out to be 1 and this will turn out to be v square by c square. So 1 minus v square by c square under square root. Now you can write this to be, now this is square root, so it is power half in the denominator. This is a square root. So what is it equal to? It is equal to 2l by c multiplied by 1 divided by 1 minus v square by c square to the power minus half. Okay, to the power minus half. This is the thing. Okay, not power half, minus half, plus half. Okay, power plus half, because it is in the denominator. So this is square root, so it will be plus half. Now it will go in the numerator. If you write this expression in the numerator, what will happen? It will become 2l by c multiplied by 1 minus v square by c square to the power minus half, because plus half in the denominator, plus half in the denominator will become minus half in the numerator. Okay, so it became minus half, 2l by c multiplied by 1 minus v square by c square to the power minus half. Okay, now again the same approximation which we have used for t parallel, that is 1 minus x to the power n is equal to 1 minus nx. But when x is very small as compared to 1, when x is very small as compared to 1, 1 minus x to the power n can be written as 1 minus nx. This is the approximation. So we will use this particular approximation here. So this minus half will go in the multiplication, and minus will become plus. So plus, and this 2 will come in the denominator over here, so 2c square. So approximately equal to 2l by c multiplied by 1 plus v square divided by 2c square. This is the expression which you got for what? This is the expression for t perpendicular. Remember this thing. This expression came out to be for t perpendicular. So this is what? This is t perpendicular equal to. Okay. This is t perpendicular equal to this much. Now, if you want to calculate the time difference, because only after we calculate the time difference, only after that the fringe can be determined. Okay. The shift in fringe can be determined only if we calculate the time difference. Otherwise, we cannot calculate it. Okay. So the time difference will be t parallel minus t perpendicular. I already told you, because for the apparatus which was shown in the figure, okay, over here, in this apparatus, the time which the light ray will, when the light ray will together travel in the downward direction towards the telescope, okay, when the light rays will together travel to the downward side towards the telescope, that particular time will be common for both the rays. This time will be common for t parallel as well as t perpendicular. So we ignore this time and the time difference will be clearly t parallel minus t perpendicular. Okay, by common sense you can say this, clearly see this thing. So time difference delta t is equal to t parallel minus t perpendicular. This is what? This is the time difference, because in the downward side when they travel together, that particular time will be required in this also, and it will be required in this also, so that will cancel out. Okay, so only the effective time difference is t parallel minus t perpendicular. This is the effective time difference. Okay, now t parallel expression, we already know what is t parallel expression. Have a look. T parallel expression has been found over here. It is like this. This is t parallel expression. Okay, and t perpendicular expression, what is it equal to? T perpendicular expression is equal to like this. Okay, so if you calculate the time difference delta t, it will be equal to t parallel minus t perpendicular. Okay, so this is t perpendicular and that is t parallel. This one is t parallel. So t parallel minus t perpendicular will be equal to what? It will be equal to 2l by c multiplied by 1 plus v square by c square minus 1 minus v square by 2c square. This is very simple algebra. You can yourself do it and have a look at it. Okay, so 1 and 1 will cancel from here. V square by c square minus v square by 2c square will come out to be v square by 2c square. V square by 2c square, 2 from here and 2 from here will cancel out, and the final expression will be L by c multiplied by v square by c square. What will be the final time difference? Time difference finally is L by c multiplied by v square by c square. This is the final time difference. L by c multiplied by v square by c square. This is the final time difference. Let us learn about observing the fringes in this particular class. So observing fringes. So we have already learned in the previous segment the time difference. Okay. Now one fact is over here that if the mirrors M1 and M2 are slightly inclined. So what it is saying is that these mirror M1 and M2 are marginally inclined. Okay, I have previously told to you that these are perpendicular to each other, and this is parallel to the ground, this is perpendicular to the ground. This is what I had told you. But in reality, this is not exactly parallel and this is not exactly perpendicular. In fact, they are very slightly inclined. Very slightly inclined. Let us say it is inclined by 1 minute. Okay, slight inclination means not even in degree, it is in minutes. Okay, so it is inclined by 1 minute. Okay, angle 1 minute angle. Why it is M2 is inclined by 1 minute angle, let us suppose, or 1 second angle, let us suppose, and M1 is inclined also by 1 minute or 1 second angle, suppose. Okay, so angle M1, mirror M1 will be slightly like this, mirror M2 will be slightly like this. Okay, very slight. It is in minutes and seconds, not even in degrees, minutes or seconds. Okay, very slight, marginally slight, we can say. Almost this is almost parallel to ground, and this is almost perpendicular to ground. Okay, this is almost perpendicular to ground, and this is almost parallel to ground, but not exactly perpendicular and not exactly parallel. Keep this thing in mind. Okay, so if the mirrors M1 and M2 are slightly inclined, what will happen? They would create a gradual phase shift. Okay, this is what you learn in the chapter waves. Okay, so they would create a gradual phase shift. This is quite evident from the fact that they are slightly inclined. So they would create a gradual phase shift, and a person would be able to observe a fringe pattern in the telescope T. So fringe pattern is observed where? It is observed in this particular telescope T over here. Okay, the telescope T which has been kept over here, in that the interference pattern is observed. Okay, so the interference pattern, fringe pattern. Okay, so fringe pattern is observed in the telescope T. Okay, the time difference in arrival of the waves in two arms would create an additional phase difference. The time difference in arrival of waves in the two arms, the time difference which we have calculated just now, this particular time difference. Okay, this would do what? This would, in addition to this particular fringe pattern shift, okay, interference pattern and shift in the fringe, this time difference in arrival of waves in the two arms, that is perpendicular arm and parallel arm. So this time difference in arrival of the waves in the two arms would cause an additional phase difference. It would cause an additional phase difference. This thing also, it is also self-explanatory. Okay, these two things are self-explanatory. However, it is difficult to find zero of the fringe pattern. Why is it difficult to find the zero of the fringe pattern? Have a look at this statement. It is difficult to find zero of the fringe pattern. Why? Because the fringe pattern 0 can be found only in ether. Okay, fringe patterns 0 of fringe pattern can be obtained only in ether, because ether is at absolute rest. But we are living on earth. So how can we find the zero of that particular fringe pattern? Because we cannot go in a ether reference frame. As the earth is moving, so we cannot go in a frame with respect to ether. Okay, ethereal frame. Okay, that is absolute rest frame or ether frame. We cannot go in that because we are already standing on the earth. We are living on the earth. So earth is an non-inertial frame in reality. Okay, if you consider it inertial, even then it is inertial with constant velocity. Okay, so fringe pattern will be different. Okay, zero of the fringe pattern cannot be observed on earth. It will be observed in ether. So one has to rotate the setup. What we can do is that we can rotate the setup. We cannot get the zero, but we can rotate the setup. And after rotation of the setup, the setup was like this. Suppose this is telescope T over here. Okay, the telescope T goes over here, so it came over here. The mirror M1 goes over here, so it came over here. The mirror M2 goes over here, so it came over here. The extended source of light goes over here, so it came over here. Okay, the mirror has been rotated by 90 degrees. So instead of like this, it is now like this. So it is like this. Okay, so the entire apparatus we have rotated by 90 degree. We have rotated the entire setup, the entire experimental setup by 90 degree. What will happen because of this? Because of this, the thing is that arms 1 and 2, that is the parallel and perpendicular arms, will get interchanged. Parallel and perpendicular arm will get interchanged because of rotation of the setup. Okay, and after they get interchanged, what will happen? After parallel and perpendicular arms are interchanged, the time difference, suppose this was the zero of fringe shift. Okay, so in apparatus 1, the fringe shift was occurring here. Okay, this was the zero of fringe shift which we could not determine. Okay, because we cannot go in an ethereal frame. So zero of the fringe shift we cannot determine. So this particular thing we cannot determine. But if we rotate the setup by 90 degree, the fringe shift will be obtained in opposite direction. Why will it be obtained in opposite direction? Because arms 1 and 2, that is parallel and perpendicular arms, will be interchanged, and the time difference will come out to be exactly the same, but the interference pattern will shift in opposite direction. So by taking the average of these two, this particular shift and this particular shift, by taking the average of these two, we can find the zero of the shift. Okay, we can find that out. Zero of the fringe shift we can find a fringe pattern. Zero of the fringe pattern we can find out by rotating the setup. So arm 1 will come over here, arm 2 will come over here. So the parallel arm will become perpendicular, and the perpendicular arm will become parallel. Okay, so this is the thing which we have done. So this is the thing which we wanted to do. Okay, in the next segment we will move further in this lecture itself. So after rotation by 90 degree, the perpendicular and parallel arm will get interchanged. We have already seen this. The parallel arm will become perpendicular and the perpendicular arm will become parallel. We have already seen this in the previous segment of this lecture. So what will happen? The time difference which was given by t parallel minus t perpendicular, time difference which was given by t parallel minus t perpendicular, you must have taken a look. T parallel minus t perpendicular. This was the time difference, right? So the time difference will now be given by t perpendicular minus t parallel, because the arms have been interchanged. Rest all the calculations will remain the same. Okay. So t perpendicular minus t parallel will be the thing which we will care about here. So as they will get interchanged, so the modulus, the sign will change. It was plus over here it was coming out to be plus. So over here it will become minus. So minus L by C V square by C square. This is the expression which you got. Delta t dash, that is the, after interchanging the arms, the time delay, the time difference is minus L by C V square by C square. Now this is clearly a negative quantity. L is positive, C is positive, C is positive, V is positive. So this is clearly a negative quantity. Okay, because minus sign on a positive quantity gives a negative quantity. So that's why negative multiplied by positive, it will be a negative quantity. So the total time delay after 90 degree rotation. Okay, total time delay, the time delay varies as the apparatus is rotated. You already know this. Okay, the time delay will vary as the apparatus will rotate. Okay, this is quite a common sense thing. So the total delay in 90 degree rotation will be given by what? The total delay in 90 degree rotation will be given by what? It will be given by delta t minus delta t dash. Why minus delta t dash? Because this is negative entity. So when we subtract it, it will become positive. So that's why minus delta t dash over here. So total delay in 90 degree rotation is given by what? Total delay in 90 degree rotation is given by delta t minus delta t dash, and it is equal to 2L by C into V square by C square. 2L by C into V square by C square. This is the total delay in 90 degree rotation. Okay. So 2L by C multiplied by V square by C square. This would cause fringe pattern to move during rotation. Okay. What will happen because of this? Because of 90 degree rotation, fringe pattern will shift. Okay. And because of this time delay, the fringe pattern will shift. During rotation, the fringe pattern will shift. And this shift in fringe pattern can be observed experimentally. This shift in fringe pattern, this particular shift in fringe pattern after exchange of arms 1 and 2, after parallel arms becomes perpendicular and perpendicular arm becomes parallel, after that the fringe pattern which will be observed, okay, it can be observed experimentally, okay, after rotation. So this is the thing. Let's look at the fringe shift. The total amount of fringe shift delta n upon rotation can be calculated from the time difference. Now have a look at this particular thing. Okay, delta n, delta capital N. Okay, so it is the total amount of fringe shift upon rotation, and it can be calculated by this particular formula, that delta t minus delta t dash, that is the total time difference after rotation, total time difference upon, after rotation, and the total time period. Capital T is the time period. Okay. Now capital T over here can be said, it can be said that it is this multiplied by 1 by t. Okay, so 1 by t can be replaced by c by lambda. How? C is equal to nu lambda. So it will be this nu is equal to 1 by t. So c will be equal to lambda by t. C will be equal to lambda by t. So 1 by t can be said to be equal to c by lambda from here. 1 by t is c by lambda from here, because this nu is 1 by t. So c is equal to lambda by t, and 1 by t will be equal to c by lambda. Okay, from here we can clearly say this. Now over here, this quantity multiplied by 1 by t can be written. Okay, what can be written? Have a look. Okay, just let me tell you this particular thing. Delta t minus delta t dash, okay, multiplied by what? Multiplied by 1 by t can be written over here. Okay. After writing this, what will happen? After writing this 1 by t can be replaced. This 1 by t, this can be written like this, and this 1 by t can be replaced by c by lambda over here. So we have replaced it by c by lambda. So this is the term which you are seeing over here. This is that term. That particular term is this. Okay. And what about this delta t minus delta t dash? We have already calculated. Delta t minus delta t dash. Have a look over here. Okay. Have a look over here. Delta t minus delta t dash is equal to 12 by c into v square by c square. Okay. So just write it that like that, 12 by c into v square by c square. Now this c will go away with this c. Okay. Now there will be cancellation and all those things. So c will go away with this c. Okay. And lambda can be written over here, and this c will cancel out. So 12 by lambda multiplied by v square by c square. So what is the fringe shift expression for fringe shift? Expression for fringe shift, that is delta capital N, that is the expression for fringe shift delta capital N. It is equal to 12 by lambda multiplied by v square by c square. 12 by lambda multiplied by v square by c square. Okay. Now the parameters that were used in one of the original experiments of Michelson-Morley, there are various parameters like L, lambda, V, C. Okay. So there are various parameters. So the parameters used in one of the original experiment of Michelson-Morley were as follows. L was 11 meter. Okay. L was 11 meter. So this particular L was 11 meter. Okay. Then lambda was 5.5 into 10 to the power minus 7 meter. Okay. 5.5 into 10 to the power minus 7 meter. So this is in meter. Keep this thing in mind. I have forgotten to write over here. This is in meter. Okay. This is in meter. Just have a look at this. Okay. So L equal to 11 meter, lambda equal to 5.5 into 10 to the power minus 7 meter, and V, that is the orbital velocity of Earth, is equal to 10 to the power minus 4 into C. Now this particular thing which we have already proved in the previous lectures. Not previous lectures, this lecture only, in the preceding slides. We have, in the preceding segments, we have already proved this particular expression, V is equal to 10 to the power minus 4 C. We have already proved this. And L is equal to 11 experimentally, L is equal to 11 meter experimentally, L is equal to lambda is equal to 5.5 into 10 to the power minus 7 meter experimentally. Okay, so this gives the following fringe shift. What is it equal to? Instead of L, in the place of L, substitute 11 over here, 5.5 into 10 to the power minus 7. Okay, v square by c square, and after substituting all those values, the fringe shift which we get is equal to 0.4. Okay, so there should be 0.4 fringe shift. So 0.4 should be the shift in fringe. After rotation of the apparatus, the fringe should shift by 0.4. That is 0.4 fringes should be shifted in the interference pattern. In the interference pattern, 0.4 fringes should be shifted. This is the thing. Okay. Now the experiment was a complete failure because this particular thing, the theoretically calculated value of delta n and the experimentally calculated did not match each other. Okay, so it came out to be equal to 0 in reality. In reality, delta n came out to be equal to 0. Why? We are going to learn in the upcoming lecture. Why the negative result? We are going to learn in the next lecture. But for the time being, just remember that delta n, which should have come out to be equal to 0.4 approximately, this delta n, instead of 0.4, it came out to be equal to exactly 0. Exactly 0. Okay. Now, everyone said that maybe there was something wrong with the experiment, in the way in which the experiment was performed. Maybe in that something was lacking. So after all those discussions and after repeating the experiment so many number of times, the delta n always came out to be equal to 0 itself. It always came out to be equal to 0. No matter in which season you do the experiment, it always came out to be equal to 0.4. So failure of the experiment was that the experiment was performed in various seasons but never gave positive results, like delta n is equal to 0.4. Instead of 0.4, no matter at what time of the year you perform the experiment, and no matter in which place of the earth you perform the experiment, and no matter whether you perform the experiment with higher accuracy as compared to this. Okay, so even after performing the experiment with very high accuracy as compared to Michelson-Morley time, even after doing that, the value always came out to be equal to 0. The value always came out to be equal to 0. Okay. So this was a failure of the experiment. This was a complete failure. Okay. But it never gave positive results. Okay. Experiment was performed in various seasons, but never gave positive results. And why it never gave positive results, we are going to learn in the next lecture. But first of all, let us understand why the experiment was performed in various seasons. Why? Why was the experiment performed in various seasons? The reason is very simple. Suppose this is the elliptical path on which the earth is revolving around the sun. Okay, and this is the sun. Suppose I am showing the sun with blue color. Okay, this is suppose your sun. Okay, this is what? This is sun, suppose. And this green colored object is our earth, suppose. This is what? This is earth. Okay, and this is sun. This blue colored object is sun, and this green colored object is what? It is earth. Okay, now in various time of the year, at this particular time, the orbital velocity of the earth will be outward from the plane of the screen. Okay, so I can show it to be like this. Okay, although it seems that I have drawn the arrow to the downward side, but imagine it in 3D. Imagine it in 3-dimensional space. So after imagining it in the 3-dimensional space, this arrow is coming out of the plane of this device. Okay, your mobile phone or laptop. This arrow is coming out of the screen of your mobile phone or laptop. So it is outward from the plane. Okay, so our orbital velocity has this particular direction outward from the plane over here. Okay, then when the earth will be here after 4 months, when the earth will be here, what will happen? When the earth will be here after 4 months, the orbital velocity will be in the rightward direction, right? Then when the earth will be over here after 4 months, the earth will be here, so orbital velocity will be in this direction. Okay, this direction is inward in the plane of paper. Imagine it in 3D. Imagine it to be in 3 dimensions. So this particular arrow goes inside the plane. This particular arrow comes out of the plane. This particular arrow is in rightward direction. And after 4 months of this, what will happen? After 4 months again, the sun will come over here. The earth will come over here. Okay. So then the velocity will be in leftward direction. So as the experiment depended, what happened in the experiment? We said in the experiment that the Michelson-Morley experiment will be performed under half an hour or something like that. Okay, so the Michelson-Morley experiment takes very less time to complete. So during that particular time, the earth will cover only a small portion of the ellipse. During that small time of the Michelson-Morley experiment, the earth will only cover a very small distance of the ellipse, and that's why we can take the distance covered by the earth during Michelson-Morley experiment time period. During that time, approximately this ellipse can be considered to be a straight line because the time is very less during which Michelson-Morley experiment is performed. So approximately we can consider the orbital velocity of the earth to be in a straight line. Okay, so that's why we had considered it to be v in the rightward direction. But when we will do the experiment in this part of the year, then the direction of v will be this, and over here if we perform the experiment over here, the direction of v will be this. Over here if we perform, the direction of v will be this. Imagine it in 3D. Okay, so this is coming out of the plane and this is going inside the plane. This is leftward and this is rightward. Okay, so at 4 times of the year, the earth's velocity is at different positions. So if we change the season and do the experiment, it again gives null result. It again gives null result only. It does the result does not vary. The result does not vary. The same result, null result. Okay, that is, we are getting 0, delta n to be equal to 0 itself. We are getting it 0 all the time. Whether you perform experiment here, or here, you always get delta capital N to be equal to 0 itself. Always. Okay. And with no matter how much precision you do the experiment, no matter how much precision you have for calculations, even after such a high accuracy of precision, the value of delta capital N always comes out to be equal to 0 itself. Okay. So this is the why this happens. Why is there a null result? That is the negative result of Michelson-Morley experiment, the experiment which failed. Okay, so why it failed and what was the problem with ether hypothesis and did ether actually exist or not? All of those questions we are going to answer in the upcoming lectures. Okay, so this lecture is over. Thank you very much.